And let's begin. So, related rates, intro, day one. Basically, today and tomorrow we're going to be doing introductions of the topic, and we will go into the more applicational parts in tomorrow. Okay, so first and foremost, the idea here in related rates, sorry, is the understanding that variables are changing with respect to time t. So all variables, in other words, are functions of t. All right. They, as time goes on, so well, sorry, I want to pick that. They might not all be functions of t. They might be constants, but constants are technically functions of t. And so as such, we're going to be working on some there. Well, before I get in there, we're going to utilize formula relations between variables, and then we're going to do some implicit differentiation with respect to t, in other words, dt. And finally, we will utilize given information to find an unknown rate. In today's work and tomorrow's work, let me actually put this into here. Basically, these are traditionally going to be geometry formulas in most cases. And in the introduction, we're going to actually only be utilizing the geometry formulas. So, formulas that must be memorized. All right, and we're gonna only, like I said, we're gonna only focus on a couple of shapes today. We're gonna focus on 3 shapes today, but there's also the other shapes that you need to know. And as we go into the other ones, we're gonna work on those ones tomorrow. So first and foremost, actually, no, I don't like how that looks.
Mister, you slide up.
Okay, red smudge. We got to continue going. So formulas to memorize. Okay. You need to copy that other stuff up. You can check the notes afterwards. All right. The most basic formulas that we need to use are for the rectangle, the square, which is really a rectangle in its own right, and the right triangle. Okay. The formulas that we're going to use is the area of a rectangle. So you should know that right off the top of your head. Now, sometimes we use X and Y. You can use what letters you want to that represent. So sometimes the problem will specifically say the length is X and stuff like that. But we'll use length times width. And the perimeter is 2 lengths plus 2 widths. I think you should all feel very comfortable knowing those. If you don't know those formulas, we're going to be in trouble for these, at least for these first 3 ones. A square is area equals S squared, where S represents the side length. So let me actually, length and width. You can use X and Y, you can use width and height, and perimeter equals 4S. Okay. On a right triangle, actually let me draw, I should have drawn those shapes first. We're going to call X, Y, and the hypotenuse Z. The first relationship you should know is the Pythagorean relationship between all 3 sides. X squared plus Y squared is equal to Z squared. Area is equal to 1/2 X times Y. The perimeter is X plus Y plus Z. These are the relationship formulas that you will be responsible in working with in tonight's homework. Okay, you're going to be utilizing those ones. However, right triangles do go a little bit more deeper, and so you'll need these for later on. You should also remember the trigonometric relationships, that if I call this my angle theta, then sine of theta equals y over z, cosine of theta equals x over z, tangent of theta equals y over x. Based on location of theta. In other words, if I put the angle up top, theta on top, then it would change. All right, so this is based on the adjacent side being labeled as x. So these are the formulas you'll need. The ones in red that I just added, you will utilize those in the coming lessons. Okay. The sine, cosine, tangent really happened. And I think I have those in day 3 or day 4. One of those. I think it's day 3 that I put those in there. And those really happen more in the applications problems when we're going to do a little bit more context. So they're pretty cool. You'll do some derivatives of trigs. The other formulas you need to know. Circle. Rectangular prism. Sphere. Now, I'm putting sphere as a different color because I'll do that. I'll note that in a little bit. Typically, these formulas are sometimes given. All right, these formulas are sometimes given for a sphere. Traditionally, on the question, it'll show that formula. So a circle. Okay. Well, I guess I don't have to show the diameter part. So if that's the circle, then you need to know that, of course, area equals what? You're not going to be given this formula. You should know it.
Pi r squared.
Pi r squared. Perfect. And the circumference is equal to?
2 pi r.
2 pi r. In a rectangular prism, where we have length, width, and height, the volume is equal to length times width times height, and the perimeter is equal to 2L, sorry, the surface area is equal to 2L times W plus 2L times H plus 2W times H. Surface area, S. For a sphere, like I said, most of the times I've seen the sphere come up, they've given you the formula. The volume of a sphere is 4/3 pi r cubed, because its units are cubic, and surface area is 4 pi r squared, which is nice in terms of doing this, because if you take the derivative of volume, you get 4 pi r squared. So it's pretty interesting that there is a relationship between the rate of volume and surface area. And of course, this is based on the image that we have a radius right there. Finally, we also have the cylinder, and we have the cone. Okay. The volume of the cylinder is just the area of the base, which is pi r squared, times height. The surface area is equal to 2 pi r squared. It's the circle on the top plus the circle on the bottom plus 2 pi r h, and L, which stands for the lateral surface area, just the area around the side, would just be that second piece, which is 2 pi r h. So sometimes the questions will only ask you about the lateral surface area. So for example, if you think of a can and you want to talk about the label, like how much goes around the side of it, because you might not be able to put things on the top and the bottom, the lateral surface area becomes very important in the cylinder. And for a cone, volume, and for a cone, you have here, this is the radius, this is the height. Volume of a cone is 1/3 pi r squared times height. So I put the star to represent that typically, the formula typically given in AP exam question. Doesn't mean always, but typically when these show up, we have this. If you know what formula to use, so the first step in many of these problems is to identify the variables and formula. So that's typically the first step in all problems, is we need to do those. Once we identify the formula, and we've labeled what we need to use, what we're using for what, the next part is where the calculus comes in. So these problems basically start off like just like your geometry problems that you've always done, but then there's going to be a rate component to the question. So I'm going to pause real quick to give some people some time to catch up right there, and then we're going to get into the actual we'll do some practice and examples. Rate of change formulas. So the rate of change formulas is the implicit differentiation of the formula / relationship with respect to t. Product rule can occur. Each derivative will have a d dt. So every single time, remember when we did those other ones and you had like times dy dx, and that only happened when you were differentiating a y, but when you differentiated the x, because you were differentiating with respect to x, you had only like just the number or just the variable. You didn't have a dx. We didn't write that. But on these problems, you're going to have d, dx, dt, dy, dt, dl, dt, dw, dt, dh, dt, dA, dt. Whatever your variable is, and you differentiate it, you have a ddt. Okay? So, you don't need to memorize these. You should be able to differentiate. They're not meant to be memorized because they should be rather straightforward or comfortable differentiations that you're going to be doing. So, let's talk about the rectangle ones. So in a rectangle, all right, and I give area equals length times width. Okay? So that's the formula. Okay? The rate of change formula is differentiating this. All right? So what you're gonna do is you're gonna take the derivative with respect to t of a of the left side and the derivative with respect to t of the right hand side. All right. So what do I get when I differentiate the left-hand side? It's, I guess you can say it's a trick question. It's very straightforward. What is the derivative of A with respect to t?
One.
Definitely never, never, number. I mentioned it just right here.
Is it d/a/dt?
Yeah, it's just d. It's just d/a/dt. It's just d/a/dt. All right. It's always going to be that. It's always going to be d/a/dt. Now, in what you have to realize is that what's not written over here, it's really saying a is a function of t, which equals L, which is a function of t, times W, which is a function of t. So that's what's really going on. So it's a prime of t or d/a/dt. So each of these variables is really just a function of t. So that's what we're really saying here, okay? Now, if the variable is a constant, then it's not a function of t, and we'll get into that more so maybe in tomorrow's examples. I don't think it happens today. That kind of takes it to the next level. If it's constant, well, something important is going to happen. So d/a/dt equals the derivative of L times W with respect to t. So how do I go about doing that side? What do I do in terms of taking that derivative on that right-hand side? You've taken derivatives of these types of, with implicit differentiation. Nothing has changed in that concept. So what do I do? What do I have to use?
Product rule?
Yeah, product rule. Perfect. It's a product rule. And so the derivative, the product rule says we have the derivative of the first part, our u, which is in this case L, and our v, which in this case is W. We get the derivative of the first, which is so it's the derivative of L, which, and how do we say that? How do we write the derivative of L with respect to t? So product rule. So what do we get? What's the derivative of L with respect to t? We almost already said the answer previously right now.
Is it LT?
Not LT.
L times T.
No, it's not a times. It's dl dt. It's the rate, the derivative of L with respect to t. So what is the derivative of L with respect to t? dl dt. That's how we say it. That's the transfer in terms of vocabulary that you got to get comfortable with. Times the second function. So times what?
W.
Times W. Plus
1. dw/dt.
dw dt. Nothing's going to be 1. I can tell you that. Nothing's ever going to be 1 in these problems. Remember, every single time you take a derivative, there better be a dt on the bottom, something dt in the answer, unless it's a constant, which I'm not covering anything with that today. dw dt times
L.
times L. So dA dt equals dL dt times W plus dW dt times L. Okay? So dL dt represents the rate of the length. So when we talk about these, the rate of change, this is the rate of L, this is the width, this is just, and this is the rate of W. So there's a relationship here. So in order to know how area is changing, you need to know 4 pieces of information. So if I asked you how is area changing? At what rate? What is the rate of change for the area? Okay. Actually, I should have written rate of change. So what is the rate of change for A? Okay. So it is understood that the rate of change for A requires 4 unknowns. So in these questions, I would have to give you 4 pieces of information to find 5. There's five variables. Each of them is a variable. dAdt is a variable. It's an unknown. dLdt is a variable. It's unknown. W, dW dt, and L. There are a total of 5. And so in any of these questions, just like in any math problem, you're going to be given 4 of them, and you're going to be asked to find the 5th. Okay. Now, the process of getting here, all right, getting this formula right here, I hope that you're not trying to just look at your notes and copy it down. Okay. I hope, but one of the biggest things that if you want to be able to pass the exam is that if you have this formula, A equals L times W, you need to be comfortable in order to find that the rate of change being dAdt equals dLdt times W plus dW dt times L. It's not going to happen on the first day for most of you, okay? So let's do the next one for this. When I said perimeter, perimeter was 2 times L, which is a constant, times L, plus 2 times W. We're going to differentiate with respect to t, the left-hand side, and set that equal to the derivative with respect to t of the right-hand side. Now, most often we don't write this dt part of it. We go directly, typically, to the derivative. All right. Now, this one is actually a much easier derivative. So what is the rate of change formula? So what is the rate of change formula for perimeter of a rectangle? Okay, so that's basically what we're finding. We're finding the rate of change formula for perimeter of a rectangle. And so what do I get? What is it? I'm going to take the derivative of the left-hand side, which gives me
2 dl dt.
the left side, your other left.
Okay, 2 dw dt.
Your other left.
Oh, dp dt.
dP dt. Yes, that's your correct left. So we got to get our formula. And it seems like, oh, but wouldn't there always be something like that? There's going to be an example. The next ones I'm going to pull up where it doesn't. So dP dt equals, now, what you were going to say?
2 dl dt.
2 dl dt. So please pay attention to what Ariana did on this one. It's 2. There's no product rule. Okay, there's no product rule here because you could do product rule, but the derivative of 2 is a constant. It's 0. Sorry, it's 0. So derivative of 2 times L is 2 times the derivative of L, which is dl dt, plus
2 dw dt.
perfect. So interesting here, the rate of change for perimeter. Perimeters, how perimeter change, the change of perimeter is based on the rates of length and width. In other words, it doesn't matter, and this is pretty interesting. It doesn't matter what the actual length is. It doesn't matter what the actual width is. The perimeter, the change, the way that perimeter changes is not based on those. It's only based on the rate of change for length and width. While area does matter. Area does require you to know what the actual length and the actual width are on top of their rates of change. Okay. Questions? All right, so the right triangles we're talking about here, X, Y, and Z with a right triangle. We're going to only focus on those first two formulas that we've talked about, the first two relationships, which were x squared. Actually, there's three of them, but I guess we do all of them. X squared plus y squared equals z squared. Now this one's interesting because you're not going to get just equals. You're not. It's going to be implicit. In other words, so that's our formula. We now want to find the rate of change formula that relates x, y, and z. So we want to take the derivative of x squared plus y squared with respect to t and set this equal to the derivative of z squared with respect to t. And what does that give us? What is the derivative of the left side? What is the derivative of x squared plus y squared? Now, we'll take it one at a time. Yeah, go.
Would it be 2 dx dt?
Close. This is, what is this problem going to require? There's another rule that we have to use in this type of problem right here, or we have to think of it as. So something that I had noticed, or something that can help sometimes, is that we can think of this as the derivative of x of t squared plus y of t squared equals the derivative of z of t squared. So you can think of them like this. It's x of t being squared. So what's the derivative of x of t squared? Think of it, if you look at it like this, what's the derivative now?
Would it be 2 and then you keep the baby same, xt?
Yeah, x. So 2x times
dx dt?
dx dt. So it's 2x of t times x prime of t. So some teachers will go over and they'll say like 2x of t times times x prime of t. They'll use like this notation right here. That is a valid notation of doing the same type of work. I find that most of my students in the past, when I've tried to do it that way, have struggled more so. So we just keep it in here in terms of the process. So when you bring the 2 down, the x stays. And now the rest of them should be very easy. The rest of the other 2 should be very easy. Plus what?
2y. 2y dy dt?
Every time you take a derivative, there better be a ddt equals
2z times dz dt.
Perfect. Now, students will do in order to make this a little bit easier to do is all the 2's cancel each other out. So x dx dt plus y dy dt equals z dz dt. How many unknowns are there here? Or how many variables are there in this formula?
3?
No, there's more.
4.
There's more.
6?
There's 6. So there's 6 pieces of information that you would want to know. X dx dt, y dy dt, z dz dt. Now, in this type of problem, typically you would need to be given 5 of them to find the 6th one. Okay. Now, these problems are a little bit more trickier because sometimes you're only given 4 and you're like, wait a minute, they didn't give me z. But if I gave you x and I gave you y, always remember you can use the original implicit formula. You can always use the original formula to find a variable. So for example, if I gave you the x and I gave you the y, then you can use the Pythagorean theorem to find z. Okay, and if I wanted to find area, 1/2 x times y. The 1/2 is a constant. So if I want to differentiate this, I get what? The rate of change formula. I'm going to differentiate the left-hand side. So what do I get when I differentiate the left-hand side?
dA dt?
dA dt equals. And like I said, this is only the second step. So we still got 12 minutes, but we haven't actually done a problem yet, just to let you know that. So we're just building the base. We're building the base right now. Now this one's trickier.
Product rule?
It's product rule. Okay, what is my u?
1/2 x?
Yeah, I like to do it like that. I like to make the 1/2 x. Some people will treat it as 1/2 times, and they'll use a parentheses. So they'll do like 1/2 times, and then they do a product rule inside. I find that most of my students don't like doing it that way, and so if you just treat the 1/2 as part of u, it works out just fine. All right, so what's the derivative of 1/2 x with respect to t?
1/2 dx dt
Times
y
plus
plus dy dt
times.
1/2 x.
There we go. So dA dt equals 1/2 y dx dt plus 1/2 x dy dt. I like to, when I write my formulas over, when I'm going to start working, I like to do it like that. Now, if you want to factor out the 1/2, you're more than happy to factor out the 1/2. I like to always put my dy dt's, dx dt's at the end of any term just to make it look a little bit cleaner. It just makes it. So there, I could have also do perimeter, but I think, I guess I'll do perimeter real fast. That one's real quick. So perimeter equals x plus y plus z. So dp dt equals dx dt plus dy dt plus dz dt. I mean, you're just taking the derivative of each of them, the sum of them. So that one's real straightforward. Now, like I said, we haven't done anything yet. We haven't done an AP Calculus question yet. We haven't done a homework question yet. This is something, finding these formulas, these 4 formulas you'll use. So in your homework tonight, you can just look at the formula and copy it down if you wish to. So you have your main formula and then you have your rate of change formula. So technically in your homework tonight, and since it's your first night and day, you can just say, okay, here's this formula and here's what I would get when I take the derivative. So you shouldn't have any mistakes in your homework in finding the derivative function. But once you've done it, now we just have to plug in the information. All right. Any questions about where we're at here so that we can actually do a problem? Oh, yeah. Rates before we get into the problem. If increasing rates have a positive derivative. So if x is increasing by 5 meters per second, then what is that telling me? If I tell you x is increasing by 5 meters per second, what have I told you?
Slope.
The slope, but it's called, we call this dx dt is equal to positive 5. So if x is increasing by 5, decreasing rates negative derivative. Area is decreasing by 2 pi centimeters squared per hour. What have I told you? What does this say? What does this tell you? It tells you dA dt. If it's decreasing, that means it's changing. Decreasing means changing. So it's not telling you what is x, it's telling you what dx dt is. It's not telling you what is a, it's telling you what dA dt is. So dA dt is equal to what?
It'll be something like negative 2 pi cm squared.
Well, just negative 2 pi in terms of the work that we're doing, yeah. Some questions we'll talk about units. We're not going to focus on the units today. We'll focus on the units in, I think, Monday's lesson. So that's something that's very important right there. So do our example. So a rectangle has length x and width y. Okay? At the instant x is 5 inches and y is 3 inches, x is increasing by 2 inches per second, and y is decreasing by 1 inch per second. Find the rate at which area is changing. Okay. So when I see this problem, the two things that stand out most importantly to me are, what is the shape? So what is the shape?
Rectangle.
Rectangle. Next thing, I need to know which formula I'm going to have to use. So where am I? What formula for a rectangle do I want to use? What am I trying to find? Well, yeah, but no, we're starting with the basic formula. So for a rectangle, what relationship do I want to use? That's always going to be at the forefront of everything. What is the shape? What is the formula?
Area.
It's area right there. Area. All right. So this tells me that area, and so I need to know area equals
Length times height.
what it says. Length is x.
To width.
Length is x, and width is y. So what should I use?
2x
No,
plus
no,
2y.
no.
X times y.
X times y. I'm just substituting the letters that are in there. All right. Now, so that's my formula. So this is the first thing I need to know. The second thing I need to know is what information is given to me in this problem. So first off, what is it asking for? It says find the rate of area. So what is the question asking me? Find what?
The rate.
Which is called what? How do we write that in notation?
The rate of change.
How do we write that in math notation that we've just done?
dA dt.
Yeah, find the ADT. So this is what I want to find. Always locate what you want to find. What am I given?
X and y.
So what are they? So x equals
5 and 2.
5. Y is equal to 3.
3.
What else am I given? I'm also given 2 other pieces of information in here.
X is increasing by 2 inches per second.
And how do I write that mathematically?
What would it be? Dx dt equals 2?
Perfect. And I'm also given,
dy dt equals 3.
boom. So now I want to find dAdt. So to find dAdt, I need to find its formula. Okay, well, we've done that. We spent all of class just finding the formula. So dAdt, and for the purposes of moving on, because I only have less than 2 minutes, it's dx dt. I just substituting the x for L and L and W times y plus dy dt times x. And finally, what am I going to do? This is the best part of this problem. What do I do now?
Plug in.
Plug in. So dA dt equals 2 times 3 plus 3 times 5. So dA dt is equal to 21. Oh, wait a minute. No, dy dt was not 3. Dy dt was not 3. Dy dt was not 3. What was dy dt?
Oh, it was 1.
Negative 1. Negative 1.
Oh.
Negative 1. So that should have been a negative 1 right there. Sorry about that. No one caught that until I caught that right at the last second. So that's 6 minus 5, which is 1. And more importantly, dAdt is equal to 1 inches squared per second. So you find it, you plug them in, and you do it. Tonight's homework is Delta Math. You're going to be doing much the same as what you're doing in this problem right here, okay? It's either going to be a rectangle or some type of triangle. You find which formula you're using, what information is given, take the derivative, plug everything in. Now, I do want to note, I could have given you dAdt before you leave. I could have given you dAdt and asked you for like, what is dy dt? All right, so when you plug it in, you might have to solve and do a one-step math problem where you have to you need to find this value right here because you're given this, and so you'd have to subtract 6 and then divide by 5. Basic math problem right there. Let you know, we've done half the amount of work. We spent a lot of extra time on that formula. I hope that you appreciate that extra time going over and going into detail how to find those rate of change formulas. It's not typically something that I would have done in the class. I would have assigned that as a big part of your own homework on your own. So I do hope you appreciate that. If you have any questions, come to office hours. There's tutoring as well, right at 2:31 in my office hours with Mr. Akers as well as myself. I'll see you tomorrow. Have a good day.